Okay, homework 4A here in Math 94E. We're going to add some fractions. We're going to deal with LCM, lowest common multiple, or the lowest common denominator if these numbers were in denominators. And then some adding and subtracting of fractions. First one, 9 over 7 plus 5 over 7. What we have to do is find the common denominator. That denominator 7, that's denominator 7. Guess what? I just found it. It's 7. So we're going to be able to keep the denominator as 7, and up top we have 9 plus 5. That's 14 on the top, right? We don't interact the numerator and denominator. We find a number for each one before that happens. Now, 7 is smaller, so I'm going to see if 14 and 7 divide by the same thing. We want a number that's bigger than 1. 7 only divides by 1 and 7. Dividing by 1 is useless, so does 14 divide by 7? Turns out it does. So we'll divide each one of them, numerator and denominator, by 7, turning into 2 over 1, commonly known as 2. It won't always reduce that way, but you need to look and see if there is any number that can divide into both numerator and denominator evenly. And of those numbers, you want the largest one that exists. That's called the greatest common factor. If you go at it with, oh, they both divide by 2, oh wait, they both divide by 3 and all that, you can get there as long as you don't miss any. But the idea here is to get it fully reduced, and something over 1 dividing by 1 we'll write as an integer. Find the LCM of 9 and 12, as though 9 and 12 were the denominators of our fractions, and then we would say, okay, what are we going to put at the bottom of our fraction? And the way to do it is to find the first number you come across that both of them will be able to divide evenly into. So I'm going to use the big 12 instead of the small 9 to get there, and it will definitely get me there faster using the biggest number. So I see if it works right away. Does 12 divide by 9? And if you divide it out and you come up with a remainder or a decimal, then no. I say that's no good. Now we go with another 12, which puts me at 24, and I try to divide that by 9, and I find that that also gets me a remainder. So now I try another 12, because these are giving me all the things 12 will work with, and I'm going to find one that also works with 9, and that does. 36 divided by 9 is 4, and you can keep that around, but here you go. The LCM is equal to 4. You can do this in other ways with factor trees. You can do this by putting the prime factorization next to each other and all that. But what you're trying to do is, 4, who said 4? Crazy, my bad, purple. Wow, it's early for purple today. But bring it out and put it to work. 4 is what happens when you divide 36 by 9, and you will use the 4 later. You'll put it to use if you're working on getting a fraction that used to have its denominator to be 9 up to having its denominator be 36. You'll multiply by 4 in the denominator to make that happen, and you'll multiply whatever your numerator is by that 4 as well. The LCM, the number we're shooting to have them both have as their denominator, is this 36. We'll see more of that when we go through full additions of fractions. So now we have the numbers 20 and 8 and 4. It's like we had 3 fractions added or subtracted, or a combination of those. And these are the denominators that we have to deal with. So we want to find the smallest number that will work for the denominator for all 3. Therefore, it needs to be the smallest number that 20 and 8 and 4 all go into. We're going to take 20 as our shortest path to get there. And we'll try 20 divided by 8, and that doesn't work. Okay, it gets me 2.5 if we do it out. So that's not going to work. I go for another 20, putting it at 40. 20 is guaranteed to divide into 40 because it's used to generate our values. I'm going to now see if 40 divides by 8. If you know your times tables, then you'll be familiar with that being a 5. So that goes, and now we must try the 4. And that's 10. You may have noticed that when you double 4, you get 8. So anything that worked in this case with the 8 was also going to work with the 4, but we can check it as we go through. The nice thing of having them come at me as 20 and 8 and 4 is 20 turned out to be the number that generates them. It's the largest. 8 is the second largest, and I look for that to work, and then I go on down the list. And if there's 4 numbers, you got to make sure all 4 of them work. But this is going to have an LCM of 40. And that would be the denominator of fractions that we would use as a common denominator. You can see that here I did work and found numbers besides knowing that they divided, and that 5 is actually what I'm going to use when it's time to pump up my 8 to 40. I'm going to do 8 times 5 and numerator times 5. And this 4 needs to be multiplied by 10 to become 40. Its numerator would also be multiplied by 10. You're getting to 40 because you have to, and you're going to increase by multiplication with that same factor there in each fraction. To keep the value of what the fraction is worth, you're getting what's called an equivalent fraction, and therefore it has the same decimal value, but it has the workable matching denominators. So now we'll put that to use here on these next two questions. 11 over 35 minus 3 over 10. So I'm starting to think of what I'm going to do for my LCM. So over here I've got 35 divided by 10. No, that's not going to work. So I give myself another 35, getting me at 70, and then I divide that by 10, and I get 7. So I know 70 is going to work with 35. 35 is what helped make it. And now I know because I divided the 70 by 10 and got a whole number of 7, that's also going to work. And so I want 70 for each of my denominators. I'd also like to turn this into plus, negative for what that one is going to be. So that's going to get me ready for whatever I have to deal with, but I can deal with positive numbers for numerators and denominators as I'm creating them, and that negative sign is there to do the job when I come back. So I take my 70 and I divide by 35. I come up with a 2. So the 70 I need divided by the 35 that I have will get me a 2, which will mean top and bottom will multiply by 2, so the value retains what it was at the same value as 11 over 35 when you double them both. It's an equivalent fraction, but it also has the 70 I need. 11 times 2 will get me 22. Now I'm on to this one, where I have 70 divided by the old 10. That's 7. So I'm going to have to multiply 10 by 7. And then the 3 up top also by 7 to retain the decimal value. 3/10 is equal to 0.3. So is 21 over 70. And there's an essential step that you have to be able to add fractions. That is, you have to keep the denominator. You can only keep them when they match. So if they don't match, there's more work to be done before you take on this step. When they do match, you keep them. You don't add them and get 140 or subtract them and get 0. You need the denominator to tell you what kind of fraction you have. So here we have 70. And when we do 22 plus negative 21, here they are. They work against each other. So I get just a 1. And because the positive 22 is stronger than the negative 21, my result is positive and I get 1 over 70. That doesn't reduce because 1 has no chance of becoming a smaller number through division as an integer in your position of your numerator. So now we're going to do the same kind of thing here. It's going to take a little bit more work to get the match of 25 and 35, but we will get there. Here's my trick on 25s. You can't use it all the time, but with 25s it works just great. If a number divides by 25, the last 2 digits have to either be 00, 25, 50, or 75. So until I see that, I'm going to keep on going with my 35s. So when I look at my 35, no. So give myself 35 more and I'm at 70. No, because I'm looking for 00, 25, 50, or 75 to show up. So we go for another 35, which is 105. No. So I go for another 35, which puts me at 140. No. And then I go for 35 more, and I do find myself now at 175. That's where I have to go with this. I have to make 175 be my new denominator. So down here, I have addition, and I have 175. Now without a calculator, this can be a lot of work. With a 4-function calculator, it can speed up the process of trying the division, finding the factors to multiply and all that, but the process remains the same. So I need 175 to be the denominator they can each use. When I go over here and I do 175 divided by 25, it will work out because I've already been through a process that shows it's going to work out. You can see that 1, 2, 3, 4, 5, 35's got me there. So that'll be helpful for the other thing. When I'm trying to divide by 25, I know it's going to work. May not be the first guess that I try. That's okay. If I guess too high, come low. If I go too low, come up higher. And we will find that it's going to work because 25 does divide into 175. 1 cannot divide by 25, doesn't even have enough digits. 17 cannot divide by 25 because 17 isn't as large as 25. So now I'm looking at basically trying to do 175 divided by 25. Here's what goes on with long division. That's pretty close to 180, and that's kind of close to 30. If it was 180 and 30, I would go with the 6. 6 times 5 is 30. Here's my 3 from 30. And 6 times 2 is 12, and I get 15. Okay. and I come around and I try and see what happens there. And although I guessed imperfectly, that doesn't mean I made a mistake. It means my guess wasn't perfect. And there's no penalty when you're guessing for not guessing perfectly. So I'm not going to tell you, what's the matter with you? How come you didn't know it was a 7? I didn't know it was a 7. I went with something, right? If you said, let me make this like 17 divided by 2, right? You just take the 17 that you see in the first 2 digits and divide by 2. Then you might even get an 8. And that would be too high. And that's also okay, because the 8 would give you 200 and you tried to take too much away. So if you came up with an 8 and that was too high, come back lower. So it's not a matter of being stupid that you need to use an eraser or at least try this thing again. It's a matter of you now gain the knowledge that 6 is too low. So you're not going to try 5, 4, 3, 2, or 1. I'm going to go, we just missed by a little. I'm going to try 7. That's what long division is. Don't let anyone tell you otherwise. You're stupid, you can't do long division right away. No, the trick is that if you find it's too low, come higher, too high, come lower until you get the one that fits, and then you're on to the next digit as needed. 7 times 5 is 35, so here's 3 from 30. 7 times 2 is 14, 175, okay, 7. That means that the multiplier that I'm going to use to get 25 up to the needed 175 is a 7, and a 7 here. So I've got to do 14 times 7. 7 times 4 is 28. There's 2 from 20. 7 times 1 is 7. Pick up the 2, you got 98. That's where this is. 98 over 175 functions the same as 14 over 25, but it's more useful for us because of what the denominator is. Same kind of thing coming up here on 175 divided by 35. Now if you look, 1, 2, 3, 4, 5 is the number that worked there for me. 5 times I used 35 to get 175, so that's how I know it's a 5. But if I try my 35 into 175, sometimes the first thing that you would guess would be correct. 1 doesn't have enough digits, 17 is too small to divide by 35, so I have to go here above the 5. It's going to be my only digit that I get. 17 divided by 3, that makes it look like 5 would give me 15 and 6 would give me 18, so it's definitely not 6. Let me try the 5. Sometimes it works out. 5 times 5 is 25. Here's 2 for 20. 5 times 3 is 15. 17, 175. And so it's not smarter, it's just that those numbers worked out a little more readily for what we're trying to do, right? Remember what I said, you could take the 17 divided by 2, and if you tried to do that, you'd say, I'm going to try an 8 because 9's too big. Or if you tried to do 17 divided by 3, like I did, come out with a 5, which is too low. You come back. So you really didn't have much chance of nailing it the first time by using 17 divided by a single digit. But we've now gotten that to be a 5 to use. So multiply the 5 here and the 5 there. 5 times 18 is going to need to happen. So I'm going to come over here. Got my 18 times 5. 8 times 5 is 40. 4 from 40. 5 times 1. It's going to get me 5. I'm going to get 90. So I'm going to put 90 there, and therefore I get 90 right here. So 175 will be my denominator, and I have to take 98 and 90. I put the larger one on top. That's positive, so they work together. That's add 188. 188 over 175. I'm pretty pleased with that. Let's find out. We could keep it like that. I'll let you know you can take your 188, as a lot of people say, oh, you must do that. That's not necessarily true. Divide by 175, it's in there once, 175. Come through and do your subtraction, get 13 over 175. So now the only thing I have to see is, does the 13 divide into 175? And so that could be tricky, but let's see. 13 into 175. Well, I put 1 there because the 13 can go once into 17. 45 divided by 13. 3 gets me 39, 4 gets me 52. No, the 13 doesn't go into 175. 13's prime, so there's nothing else that 13 divides by besides 1 to try and work that with. So I can get you this 188 over 175, and that's fully reduced. Or if you need to have it as a mixed number, you can now come back here and get me the full 1. And the remainder, let's see, what did we do? Oh, let's see. We're going to finish this out. We got our, we tried to do reduction there, sorry. We had 13 left over 175, also acceptable. 175 is what we divide by, that's our denominator. 1 is the whole part, the integer, and the remainder of 13 goes there, no further reduction. I'll pick up problem 6 in just a minute. Okay, so now we're working on problem 6 here in 4a, and what we have here is 9/10 plus 1/2 minus 1/3. So what we have is we have 3 fractions. 10 is the largest of the denominators. That'll be the one guaranteed to take the fewest steps to get me to where they all can work. So we'll take a look here and see what comes out of it. We've got 10 divided by 2 works to give me a 5, but 10 divided by 3 won't. So that's not it. 10 more. 20 divided by 2 will get me 10. 20 divided by 3, no. So you got to get 10 more to try 30. 30 divided by 2 will eventually get me 15. You can do the long division. 30 divided by 3 gets me 10. 30 is going to be it, LCD. The 30 here works with 3, 30 here works with 2, 30 came from the 10s. So I'm going to go with an LCD of 30. All of them have to become equivalent fractions with their denominators based on being 30. Now this is plus the second one. Now this minus the third I'll turn into plus, and I'll put the negative sign up in the numerator waiting for the number to come along and join it. Okay, what do we have now? We've got a 30 divided by 10, right? If we take our 30, divide by 10, come out here with a 3. That's why these are multiplied by 3. 10 times 3 gets me the 30 that I must have. 9 times the 9 that was there times the 3 I just created will get me 27. Okay, now we got 30 that we need, divided by the 2 that we had, and that gets me 15. You can do the long division, but 15 is what that needs. So 2 times this 15 will get me to 30. The existing 1 times 15 will get me 15. So come out here with 15. And behind the minus sign, and here as a negative fraction with 30 as its denominator, I have one more to make. I have 30 that I need, divided by the 3 that I had, and that calls for me to have a 10. 3 times 10 will get me to the 30 as needed, the existing 1 times 10. 10 over 30 is what this is making. It has the same value as the old 1/3, but now it has workable denominator. They all have the same denominator of 30, which will stay. That's why even before I get to work on doing work with 27, 15, and the 10 as they are, I establish that 30 is my denominator that they all have in common. So I just keep that denominator. Huge thing to keep in mind. 27 plus 15 gets me 42 plus negative 10. Subtracting now 42, I added this 2 positives together. 42 minus 10, still strong on the positive because 42 is stronger. I get 32 over 30. Each divides by 2. 30 is smaller, but 32 doesn't divide by 30. Next I come to 15 and 10. These are all things 32 doesn't divide by. And then 6 and then 5. And I do reach 2. And they do both divide by 2. So I get 16 on top and 15 on the bottom. If I took my 16 and divided it by 15, you'll find a full 15 in there and a remainder of 1. It's one step on the set of 15 that would have gotten us up from 1 to 2. So 1 and 1/15 is also acceptable. How much thicker is a 1/2-inch cell phone than an 8 25 inch cell phone? So how much more? How much extra? What's the difference? Wait a minute, that last one helped a lot. What's the difference between the two? The difference is something we find when we do subtraction. So I'm going to have subtraction here. And how much thicker is this 1/2 than that 8 over 25? Telling me this one is extra. That's the big one. Let's start with that. 1/2 here. Minus however much was there at the 825. Now if you want to picture this, imagine you take blocks of soap to make exactly the size as you have for each of the cell phones. And then you would put the smaller one next to the bigger one and slide it over. How much extra height does it have? What if you could take a laser or some kind of sharp cutting tool and right at the top of the small one, slice it off to take the same amount off each. This loses its whole self and this loses its bottom part. How much is left over? So what we're looking at is we might have this half might be this big, and maybe the 8/25 is there. You come and you slice over here so that those are next to each other doing the same height. And you pull off the top. How much did you pull off? How tall is that extra? It's subtraction, right? So what we have now is 2 and 25. 25 is bigger. 25 doesn't divide by 2. 25 more makes 50, does divide by 2, so I'm going to go with 50. Okay, I'm going to go with plus and make that negative. Let's go see what we got. We've got to have a 50, right? So we take our 50, divide by our existing 2, and this guy needs 25. So we multiply 25 times each. This will get me right to the 50 that I need. 1 times 25 gets me 25 over 50 for my old 1/2. 50 divided by 25 winds up being 2. So 2 is the multiplier, the factor as we call it. 2 times this, 25 times 2 will make the 50 that I must have. 8 times 2 will keep the balance of it's still worth what 8 over 25 was in terms of a decimal, 0.04. Right, so no, let's see, 8 over 25, nope, that'd be like 0.32. But anyway, it's gonna keep the same value, doubling them both. We got a 16 here when we did our 8 times 2. So now we're keeping the denominator. The 3 words you must know about adding or subtracting fractions is keep the denominator. If you're not in a position presently to keep the denominator, go back and do the work necessary to make them match. You can't keep something when they don't match. If you're saying, I guess I'll keep the 2 because I saw that first, or I'll keep the 25 because it's bigger, that's no good. You got to keep one that matches. So 50. Now we have 25 positive and 16 negative, so they work against each other, so we're definitely subtracting. 5 minus 6 I can't do. I need to turn my 25 into 10 and 15. If you know 15 minus 6, awesome, you're going to get a 9. Again, I don't have 15 fingers, but if I put 4 more on that to make 10, then 4 more on that will make 19. 19 minus 10, I can get the 9. 1 minus 1, I don't have anything in the tens digit. I have that. It's a word problem that asks you how many inches, so your answer will include inches. Careful and connect math. If it says the word inches on the screen and it just has a box for you to fill in, then the answer would be 9 over 50 and use their inches. You don't want to have it be 9 over 50 inches that you type in and then throw their inches, because that gets into this whole other mess about inches is there twice, which means squared inches, and measures the wrong stuff. Okay, this one's going back, as is this one, to continue to work on multiplication and division of fractions. The first thing is these aren't fractions, these are mixed numbers, and I don't want to just kind of use pieces of it like that, and I don't want to use FOIL. If you've used FOIL before, you'd have the opportunity, which I'm not going to do all the way out, to go 10 times 3, 10 times 6 sevenths, half times 3, half times 6 sevenths, and add up those 4. And you may see that if you go back and look in, I think it's lesson or even homework 3, that's demonstrated, but that's not what we're here to do. We're here to make this into a workable fraction. So I take my 10 full ones and multiply by 2. Gets me 20 pieces plus the old 1 piece. So I have 21 still over 2. See, the denominator didn't change. How we're breaking up that fraction? 2's. Halves. Now this one uses sevenths. So here we go. 3 full ones. They get smashed down into 7 pieces each. So 3 times 7 gets you 21 plus the old 6. 21 plus 6 gets me 27, and that's over 7. So this is what I now have to do with my multiplication. Now I don't want to do 21 times 27. Sometimes I'll have to, or 2 times 7 is not so bad. But 21 and 2 don't divide by the same thing. 21 and 7 do. They both divide by 7. So I'm going to divide my 21 by 7 and my 7 by 7. Right? This is going to become 3. This is going to become 1. Do write the 1 so you know that you're done with that. And you can't reduce the 1 anymore. Now I take a look at my 27. Does 27 reduce by the same number as 2 does? The answer is no. They don't both divide by a number larger than 1, and you can't reduce a 1. I always call that 1 and done. So we've got 3 times 27 representing what's going on in our numerator, and 2 times 1 in the denominator. 3 times 27. 3 here, 27 there. 3 times 7 is 21. Here's the 2 for 20. 3 times 2 is 6. 81. 81. 2 times 1 is 2. That's fine. If you want to do that out because you can't stand it being an improper fraction, here's what you would have to do. The 8 itself can handle having 4 2's. 4 times 2 is going to get me 8. Subtract, bring down the 1. The 1 can't handle it, so you get 40 and a half. There you have it. So that's the use of converting your mixed number into an improper fraction. We do that for multiplying, we do that for dividing. We don't need to do that for adding and subtracting. Some teachers teach it that way because they say, oh good, I don't have to teach much, I just have to tell them, do this, and it makes for a lot of work. Instead, we're going to think as a teacher, and you as a student are going to think, how am I going to deal with these? When they're multiplying and dividing, absolutely great to use the improper fraction. When you're adding and subtracting, you're doing a lot of multiplying and dividing that you don't have to do if you don't know that they can be done as separate pieces. So let's look at this now. This is division. So division will later turn into a multiplication problem, but that's when we have two fractions. We don't have them in fraction form yet. So 1 times 5, 5 new pieces plus 4 old, that's 9, still fifths as the denominator. Division remains here for this one step. 2 times 7 will get me 14 new pieces plus the old 4. 14 and 4 gets me 18, and there's still sevenths. Now, anytime we're dividing fractions, we keep the first fraction exactly as it is. We change to multiplication by the reciprocal of the second. As you might recall, the first fraction tells you what you're dealing with, and the operations happen using the second fraction. So that's when we make our manipulations into something we can manage. 9 and 5 don't reduce. 9 and 18 each divide by 9. So that becomes a 1, which I write. That becomes a 2. I might be done, but I don't know that until I take a look at 7 and 5 don't reduce by anything. 7 and 2 don't reduce by anything. 1 doesn't cause any reduction. So we have 1 times 7 over 5 times 2, which is a 7 over 10. 7 is a prime number. Does 10 divide by 7? No. It is a fraction. It's not an improper fraction, so we're good to stop it right there. How did I know that was going to be a fraction? Maybe I didn't. How do I now know that I should have gotten a fraction? This is a number smaller than 2 divided by a number bigger than 2. I don't have a full number, a full passage through, so I'm definitely going to come up less than 1. If when you're dividing you have a larger number to start here, then there you're going to come up higher than 1. All right, this one, as you can see, is 2 plus 1 over 14, and then it's plus 5 plus 3 over 14. I'll change the order of them. 2, then the 5, then the 1/14, and the 3/14. So these two are straight up going to be added. 2 and 5 have always made 7. They still do. Keep the denominator, which they have matching already at 14. 1 and 3 makes 4. So now we got 7 and 4 over 14. If 4 over 14 is fully reduced, we are done. It's not. 4 divides by 4, 2, and 1. 14 doesn't divide by 4, but 14 does divide by 2. So we keep the 7. 4 over 2 is 2. And 14 over 2 is 7. 7 and 2 sevens. And that's done. That did not have denominators that were different, but it went through the process of let's get the 5 and 2 together up front, let's get the fractions together at the back, and then as we get to more challenging problems, we'll see that even after that happens, we'll be able to focus our work on the fractions in the back while the integer sits out front, waiting to see if it has to do anything such as absorb a 1 because we got too big a fraction, or give up a 1 because we're subtracting too much. Otherwise, that 7's part of our answer. The only way these things go sometimes is the 7 will go up to 8 if you get too big of a fraction. The 7 will go down to 6 if you're subtracting away too much. But there the 7 stayed all the way through. About to get involved with the next two problems that deal with borrowing and carrying with fractions, and lots of people have a lot of trouble with this. Some teachers bail out and say, make them both into improper fractions, then do the work and then bring it back. And that's not necessary, although that's an option if this totally doesn't work for you and you don't mind all the big numbers it creates and then needs to wash back down. But here's how I would do this one. We have 3 plus 1/4, plus we have a -1, and we have a -2/3. Now we'll take the 3 up front and the -1 second, the 1/4 third, and the -2/3 fourth. What that is me taking the 4 terms, the 4 things that I have added here, and changing the order so that I can deal with 3 minus 1, 3 plus -1, giving me 2, and then back here I still have 1/4 plus -2/3. So now that equals, when I come here, 2 plus a pair of fractions, the second one negative. 3 and 4. 4 is bigger. Does 4 divide by 3? No. 4 more is 8. Does 8 divide by 3? No. 4 more is 12. That does divide by 3. So I'm going to put 12s in here. And now, what I have is I need a 12 divided by the old 4. That one needs to be tripled, or here with a 3, top and bottom, so that that old 1/4 is now going to be working and more functional as 3/12. I have a 12, divide by 3, I get 4. That means I need a 4 to get this job done of multiplying top and bottom by 4. The old -2/3 has a 12 on down there as its denominator, but 2 times 4 with a negative is -8. So what happens here? We got 2 plus 3 minus 8. They work against each other, so I do subtraction to find out what's the difference between 8 and 3, and that's a 5. So I have a 5 here. The -8 is stronger than the +3. It's a larger absolute value. Therefore, my sign of this 5 is negative when I put it over 12. The 5 is where the negative is, the 12 is positive, or at least it's just sitting there without a sign. Okay, 2 plus -5/12. What can we do here? Well, what we're going to do is we're going to break the 2 up. Whatever number it is, I'm going to break 1 off. Breaking 1 off the 2, it becomes 1 plus 1 plus -5/12. Here's the first one. This 1 goes in as 1/1, right? So I'm going to actually write that for you so you can see it as you're looking at this, plus -5/12. All right, so the one that's full stays like this, and now I get to say, what's the lowest common denominator? 1 and 12. 12 is biggest. Does 12 divide by 1? Of course it does, right? That's the good thing about borrowing and carrying here. 1 is going to be very simple to work with as long as you don't let it scare you off. So we're going for 12s for these 2 denominators. They're both going to be 12s. So we got 1, plus we've got something over 12, plus we've got a negative something over 12. All right. We need 12 divided by 1. I need to multiply top and bottom of this by 12, just to find why the 1 is in perfect form if I make it as 12/12. I'm going to stick with the process, although you might know the -5/12 is going to stay unchanged. 12 divided by 12 gets me a 1, so that lets the 12 stay, and 5 times 1 makes a 5. The negative sign is already there, so I've got that. There are ways to shorten this process, but shortening it can take people away from understanding it, and it could kind of say, look at the magic I did, and you'll say, yes, I'll memorize that magic. I haven't found through the years that works particularly well. So we definitely have this 1 here as the whole number, plus we have something over 12. Now 12 minus 5, they work against each other, so we get a 7. And the 12 is positive with the -5, so the 12 is stronger, so when I make my 7, it's positive, and therefore I get 1 and 7/12. Both of these are positive values, the +1 and the +7/12, and that's done. So you can slow it down, rewatch it, ask me when we get in contact, but that's a way to do it. You don't need to make it into improper fractions. Next one is adding 1 and 4/5 to 4 and 2/3. 1 plus 4/5 plus 4 plus 2/3. It'll work better if I have the 1 and 4 first for my 5 it's going to make, plus the 4/5 and the 2/3. I mean, pretty much what I did is I swapped the 4/5 and the 4's locations so that we can get 1, let's clear these out here, 1 plus 4 for 5. And then back here I do have fractions to deal with. I still have 4/5 and I have 2/3. So I have 5 plus a pair of fractions. 3 and 5. 5 is bigger. Does 5 divide by 3? No. Does 10 divide by 3? No. 5 more. 15 divide by 3? Yes. So I'm going to put 15 in there as my LCD. So 15 that I have divided by my old 5 tells me I need to use a 3 here. My old 4/5 with a 15 in its denominator must have a 12 as its numerator. 15 divided by 3, that's a 5. So my old 2/3 has a 15 in its denominator. It needs 2 times 5 to get me 10 as its numerator. Now the 15s are going to stay. The big 5 is going to stay. We're going to add 12 and 10. Big 5, 15. 12 plus 10 is 22. I can't keep that. So what I'm going to do is I'm going to take that equals 5 plus, I'm going to do 22 divided by 15. So take my 22 and divide by 15. You'll notice that I came out of here with a 1. 1 times 5, 1 times 1. 22 minus 15, you might not know. Do you know 12 minus 5? Maybe. I don't have 12 fingers. Maybe if I put this down to 10 and 12, 12 minus 5, I still don't know. If you know it's 7, that's good. But 5 more here makes it into 10. 5 more there makes it 17. 7 minus 0 is going to give me 7. That's my remainder, 7 over 15. So I've got a 1, and I've got a remainder of 7 over 15. 5 and 1 will make 6 with 7 over 15. Okay, so we may have to borrow 1 if we don't have enough because of the negative fraction. We may have to push 1 over with carrying if we get a fraction that's improper at the end of our process of adding what I call like terms. We have like terms when we have integers, and we have like terms when we have fractions with the same denominator. Like terms will come up a lot in the algebra work we'll be doing here. All right, 5 minus 2 over 9. How about the 5 being 5 over 1? That's definitely one way some people could do it, right? Multiply them both by 9, 45, and then you're into that whole, mixed number thing. I want to let you know that's okay if that's the way you do it. How about the way we've been doing it, though? The way I've been working on it with you. 5 is whole plus negative 2/9. All right, because I don't have any fraction here to get rid of the 2/9 with subtraction, I'm going to have to turn my 5 into 4 plus 1 plus then the negative 2/9. 4 plus 1 over 1. You don't have to write every step, but you have to be able to understand what you're doing so you can apply it in other ways. So I'm going to write the 1 over 1 step right there, plus negative 2 over 9. Now, 4 is done. 4 will be in my answer. Let's deal with the fractional part, though. 1 over 1 plus negative 2 over 9. So I'm focusing only in that little spot. 9 is bigger than 1, and that'll be perfect for my denominator. The second one is negative. Okay. Ones are pretty simple work to deal with. Like I say, you don't get scared off with them. Don't try and memorize tricks and traps. Just try and understand that we have 9 divided by 1. That's why this needs to be a 9. And we wind up with 9 over 9 in place of my old 1. 9 divided by 9 gets me a 1, so I multiply 9 by 1. I multiply that 2 by 1. And that's why I wind up here with the negative being there with a 2. 4 is good. Right, I told you the 4 would be there at the end. Then we got to go 9 plus negative 2. So we subtract 9 minus 2, we get 7. And the denominator is 9. It's 4 and 7/9. Cut a 13 and 2/5 inch board into 4 equal pieces. So how do we cut a board up? When we are cutting up a board, are we adding up the board? Are we dividing the board up? Are we multiplying the board up? Are we subtracting the board up? We're dividing the board up, right? The only one of those that makes any sense is we're taking the board, making it into equal smaller pieces, is we're dividing the board up. We're taking the board, which is 13 and 2/5, and we're dividing it. There's our board, and kind of doing that to it. So we got 4 hopefully close to equal pieces. We definitely want them equal if that's what the measurements require, but we're dividing that into 4 equal pieces. So we want to divide this thing by 4. So So we can't work with that as a mixed number. So we're going to take 13 times 5, get 65 plus 2. You got 67 over 5. Divided by 4, make that a fraction, 4 over 1. 67 over 5 represents how much wood we have when we get this thing started. In order to do manipulations and get the work done, instead of trying to divide 67 by 4, which creates a decimal, and then have a 5 in the bottom, we're going to go ahead and multiply by the reciprocal. Instead of letting the 4 make 67 weak by division, we're going to let the 4 make the bottom strong, multiplication. Instead of letting the 5 stay there with the 1, we'll put the 1 up top, so it's 2 switches. It's change to multiply and 1/4. 67 and 5 don't reduce. 67 and 4 don't reduce. 1 doesn't reduce with anything, so we have to go with 67 over 20. Okay, so that's how long each piece is. Instead of having the 67 over 5, we have 4 times as big a number in the denominator with that 20. We take our 67 and we divide by 20. How do you know to do this? It's because this started as a mixed number, then our answer should also result in a mixed number. We go ahead and we get them 3 here, and that's going to create 60. And then we have 7 left over, so we have 7/20. So it's 3 7/20 inches for our answer. And what happens is the 3 inches times 4 pieces gets you 12 inches. 4 times that 7 gets you 28 over 20 for the rest of it. 28 over 20, when that reduces by 4 is 7 over 5. So you'll see 7 over 5 is 1 1/5, and we get to the 13 2/5. So it is correct. But this is a division problem that requires us, after setting up the division in the right order, make the mixed number into an improper fraction, make the integer into a fraction of 4 over 1, proceed to keep the first number when we multiply by the reciprocal of the second, and we're ready to get this done. And that wraps up the work I've been presenting here on homework for